Good morning, dear students. Myself, Dr. Lipika Samanto, Assistant Professor, Department of Chemical Engineering of Holy Institute of Technology. Today, I will discuss flow through a circular tube in momentum transport. So, last day I already discussed the various practical exam, solving this practical example with the help of different cell momentum balance steps and taking the boundary limits conditions in these particular cases. So here the first one steps are first choosing the coordinate system in a particular cases. Then we select some assumptions to solve the problem. Third one, we formulate various type of momentum equation for momentum balance. After that, sum up all the momentum equations, and then we assume some conditions, and finally we got the cell balance, and then integrating this equation. After that, integrate this equation, we obtain one integrating constant. To solve the integrating constant, we taking the boundary conditions in a particular cases, and applying the boundary conditions, we get the value of the C1 and put the value of C1 in that equation, and finally we got the shear stress. After that, we compare this equation Newton's law of viscosity and further import the Newton's law of viscosity in this equation and further integrate this equation. Finally, we got the velocity distribution, and again we obtain another integrating constant. So for these cases, particular cases, we assume boundary conditions, put the value of boundary conditions in that equation, and finally we got the value of integrating constant. And putting the integrating constant on that equation, finally we got the velocity distribution for particular cases. Here we first consider the steady state laminar flow of a flow of constant density rho in a very large tube of length L and radius capital R. Here the fluid is flowing in z direction, which is also direction to the force of gravity, and tube is assumed very long, so we want to assume that there is no end effect. Next, we assume some assumptions. The first assumption is the fluid density and viscosity are constants. System is in steady state. The flow is laminar flow and fully developed flow. And last one is the Newton's law of viscosity is applicable. And we also ignore that the entrance of tube and the exit of the flow will not be parallel everywhere in the tube surface. After that, the problem is based on the cylindrical coordinates. The we can choose first one, the cylindrical coordinates. Then the fluid is moving in the z direction. So here the velocity distribution Vz into R, and the j tensor subscript is equal to z and I is R, and the only relevant stress is tau Rz, and the jet momentum balance will be performed with a differential in the r directions, and the force of gravity is in the same direction of the fluid flow, so it will be the positive. Next, consider the cylindrical cell thickness delta r and length capital L. After that, we formulate various components of the momentum balance. First one, rate of momentum in across cylindrical surface at r radius, 2 pi r into L into tau rz at r, and rate of momentum out across the cylindrical surface at r plus delta r equals to 2 pi r L into tau rz at r plus delta r, and rate of momentum transport in across the annular surface at z equals to 0 equals to 2 pi r delta r into Vz into rho into Vz at z equals to 0. Similarly, rate of momentum out across the annular surface at z equals to L equals to 2 pi r into delta r into Vz into rho Vz at z equals to L. After that, we consider the gravity force. So, gravity force acting on the cylindrical cell equals to 2 pi r into delta r into L into rho g. Next, the pressure force acting on the annular surface at z equals to 0, 2 pi r into delta r into P0 at the entrance of the tube. And next, the pressure force acting on the annular surface at z equals to L means the exit of the fluid flow of the long tube equals to 2 pi r into delta r into PL. So by adding the contribution of the momentum balance, so rate of momentum in the cylindrical surface at r minus rate of momentum out at cylindrical surface in r plus delta r plus rate of momentum in the annular surface at z equals to 0 minus rate of momentum out at annular surface z equals to L plus pressure force acting on the annular surface at z equals to 0 minus pressure force acting on the surface at z equals to L plus gravity force acting on the cylindrical cell equals to 0. So, first one is the 2 pi r L into tau r z at r minus 2 pi r L into tau r z at r plus delta r plus 2 pi r into delta r into Vz into rho into Vz at z equals to 0 minus 2 pi r into delta r into Vz into rho into Vz at z equals to L plus 2 pi r into delta r into P0 minus 2 pi r into delta r into PL plus the gravity force 2 pi r into delta r into L into rho g equals to 0. After that, we assumed the fluid is assumed to be the incompressible. So, Vz is same at the entrance of the fluid flow and the exit of the fluid flow means at z equals to 0 and z equals to L. Thus, the rate of momentum in across annular surface at z equals to 0 and rate of momentum out across the annular surface at z equals to L will be cancelled out. So finally, we obtain the setting of the cell balance 2 pi r L into tau r z at r minus 2 pi r L at tau r z at r plus delta r plus 2 pi r into delta r into P0 minus PL plus 2 pi r into delta r into capital L into rho g equals to 0. After that, dividing the constant term. What is the constant term? 2 pi r into delta r into L and taking the limit, the thickness of cell delta r approaches 0 and also the derivative from of this equation d of r tau rj divided by dr equals to P0 minus PL divided by L plus rho g into r. While it's the algebraically equal to the above equation, one substitution of the modified pressure can be generalized. What is the modified pressure? Modified pressure small p is defined as capital P equals to small p plus rho gh, where g is the distance in the direction of the opposite of gravity. In this problem, small p equals to p minus rho gz. Here, z is the distance in the same direction as gravity. So, minus sign has been considered. So, finally, we integrate this equation and tau r z equals to r into small p0 minus small pl divided by 2 capital L plus C1 by R. So we obtained the value of CR taking the boundary conditions. Tau Rj tends to infinity at R equals to G. So value the boundary conditions in that equation, and finally we got the value of C1 equals to 0, and which is impossible. So tau Rz equals to R into small p0 minus small pl divided by 2L. Then the tau Rz means shear stress is comparing and applying Newton's law of viscosity. What is the Newton's law of viscosity? Tau Rz equals to minus mu into dvz by dy. The putting the value of tau Rz in that equation, and finally we got the d into vz by dr equals to minus small p0 minus small pl divided by 2 mu l into r. After that, again integrating the equation, and Vz equals to minus small p0 minus small pl divided by 4 mu l into r square plus c2. So then again we obtain the value of integrating constants into taking the boundary conditions in liquid solid cases at Vz equals to 0, at R equals to capital R. So putting the value, the boundary conditions of that equation, and finally got the value of C2. So C2 equals to small p0 minus small pl into capital R square divided by 4 mu L. So putting the value in that equation, value of C2, and finally we got the velocity distribution of flow through a circular tube equals to small p0 minus small pl into capital R square divided by 4 mu L into 1 minus small r by capital R whole square. So the velocity distribution for laminar in the tube is parabolic. After that, we obtain the different cases. First one is the maximum velocity, second one is the average velocity, and third one is the mass rate of flow. When we got the maximum velocity, the maximum velocity Vz max equals to 0 occurs at small r equals to 0. So the value of small r putting in the velocity distribution equation, and finally we got the maximum velocity Vz max equals to small p0 minus pl into capital R square by 4 mu L. Then we obtain the average velocity. The average velocity is obtained by dividing the total volumetric flow rate divided by cross-sectional area. So average velocity equals to integration 0 to 2 pi integration 0 to r into Vz into r into dr into d theta divided by integration 0 to 2 pi integration 0 to r into dr into d theta. To put the equation of Vz here and also the value of Vz here, and finally we got the value of average velocity small p0 minus small pl into r square divided by 8 mu L, which is compared to the maximum velocity, and finally we got the average velocity equals to half of maximum velocity. And last one is the mass rate of flow. Mass rate of flow, small w, is the product of the cross-sectional area pi into capital R square into density rho and the average velocity. So w equals to pi into capital R square into rho into put the value of average velocity means small p0 minus small pl into R square divided by 8 mu l. So finally we got the equation small w equals to pi into p0 minus pl into r to the power 4 into rho divided by 8 mu l, which is also called the Hagen-Poiseuille equation. So from when we derive or when we solve the flow through a circular tube in momentum transport, we also got the Hagen-Poiseuille equation. So today I stop here. Thank you.